Hello my friends, and welcome back to the You Can Do TV channel. The third Bosphorus Bridge and Northern Marmara Highway project is an ambitious infrastructure endeavor aimed at enhancing Istanbul's connectivity and addressing its heavy traffic congestion. Key milestones have been achieved in both the bridge and surrounding infrastructure. The reinforced concrete decks for the approach viaducts on both the Asian and European sides have been completed, providing structural integrity for the vehicle lanes. In addition, the assembly of a 1,000-ton capacity derrick crane was successfully finished. This crane played a pivotal role in lifting and positioning massive steel bridge components. For instance, the third steel deck, which weighs 940 tons, measures 24 meters in length, and spans the full 59-meter bridge width, was lowered into position using a floating crane with a carrying capacity of 1,800 tons. Before installation, the derrick crane conducted lifting tests to ensure safe handling of these immense bridge segments. The assembly of the bridge's suspension system, essential for bearing the bridge's weight, is also underway. This includes the inclined suspension ropes, one of the two key systems that will support the bridge. A significant step in cable installation was the completion of the catwalk structure, used to assist in pulling the main cables across the span. Once the catwalk was finished, work began on the main cable pulling, a critical phase where cables are stretched across the bridge from both ends simultaneously to distribute load evenly. Meanwhile, progress continues on the European side sections of the Northern Marmara Motorway, with multiple viaducts under construction. Reinforced concrete work for the viaduct piers is advancing steadily, with various piers in the E2 section at different stages of completion, ranging from 33% to 98%. The eighth steel deck, measuring 24 meters in length and 59 meters in width and weighing 940 tons, has been successfully assembled. The construction of the catwalk was also completed, enabling the installation of the main cables that will support the bridge. Following the catwalk completion, tower saddles were installed on both the European and Asian towers, preparing the bridge for main cable support. Shortly after, the assembly of the 14th steel deck was completed, and the cat tracks were installed, allowing the main cable pulling operation to commence simultaneously from both sides. The placement of the tower saddles, located on each bridge tower, marks another important achievement. These saddles serve as a base for the main suspension cables, which will support the bridge deck. Additionally, the assembly of multiple steel bridge decks has been completed, with each deck segment weighing around 940 tons. With the cat tracks fully installed, the project proceeded to the crucial main cable pulling phase, a synchronized operation from both the Asian and European sides. One of the foundational achievements includes the completion of the V20 leg foundations on the Asian side in the A1 section of the Northern Marmara Motorway. These structural bases support the bridge and ensure stability for the spanning highway segments. The project's main cable pulling process, essential for the bridge's suspension system, has reached its final stages. Following the installation of the catwalk, or kedi yollerini, 85% of the two main cables weighing a combined 13,000 tons has been installed. A critical aspect of the bridge's support structure, the inclined suspension ropes, has also seen significant progress. These ropes, totaling 128 in number, are key to stabilizing the bridge deck and managing the load distribution across the structure. Concurrently, work continues on installing the massive 10-meter steel upper beam panels, each contributing to the overall resilience and integrity of the bridge. This step is particularly intricate as it aligns with ongoing cable installation efforts requiring synchronized timing and meticulous precision. The main cable pulling process, one of the most demanding phases of the project, was successfully completed with an impressive 71,645 kilometers of rope pulled to achieve the tension and alignment necessary for the bridge's structural needs. In parallel, the installation of inclined suspension ropes, which has now reached approximately 5,500 kilometers of cable, is nearing completion. This system of cables is crucial in distributing the bridge's load between the main support towers and the suspension deck, maintaining stability under dynamic conditions such as heavy traffic and wind. Out of the planned 59 steel decks, 42 have now been successfully assembled and welded, bringing the project closer to its goal. The bridge's construction has now narrowed the gap to just 391 meters between the Asian and European sides, marking a major milestone as the project nears structural unification across the Bosphorus Strait. Key progress has also been made in the northern Marmara Motorway's E2 section on the European side, with the reinforced concrete manufacturing of the V19 and V16 legs completed in full. The installation of the massive lifting gantry cranes has also been accomplished. Consisting of two parts and weighing a total of 380 tons, these cranes boast an impressive carrying capacity of 3,000 tons. These gantries play a vital role in lifting and placing the bridge's massive steel decks with precision. Recent efforts have focused on finalizing the welding process across multiple deck segments. This includes the critical 41st and 42nd segments, as well as segments ranging from the 34th to the 55th. Each of these welded sections forms a crucial link in the bridge's overall structure, enhancing its resilience and ensuring seamless load distribution. These developments bring the project ever closer to its final completion, with only a few remaining segments before the bridge's two sides meet, creating a new continuous pathway across the Bosphorus. The project encompasses a total of 115 kilometers of infrastructure, including highways, access roads, viaducts, tunnels, and, notably, the third Bosphorus Bridge. Also known as the Yavuz Sultan Selim Bridge, this bridge is set to become a record-breaking structure with several unique features. It will be the world's widest suspension bridge, measuring 59 meters in width. Spanning 1,408 meters, it will also be the longest suspension bridge with an integrated rail system, enabling both rail and vehicle transit. Additionally, it boasts towers reaching 322 meters in height, making them the tallest towers of any suspension bridge globally.
Sheet pile driving is a crucial process in bridge construction that involves the installation of interlocking steel sheets, known as sheet piles, into the ground to form a continuous barrier. These sheet piles are commonly made of steel due to its durability, strength, and resistance to corrosion. The primary purpose of sheet pile driving in bridge construction is to provide temporary or permanent support to excavations, retaining walls, and foundation structures. Sheet piles are installed vertically or at a slight inclination into the ground using specialized equipment such as vibratory hammers, impact hammers, or hydraulic presses. The chosen method depends on various factors such as soil conditions, environmental constraints, and project requirements. The driving process involves carefully positioning the sheet piles at predetermined intervals along the bridge's alignment. The sheets are then driven into the ground using the selected hammer or press, which transmits a powerful force to the top of the sheet pile. This force drives the sheet pile into the soil, allowing it to penetrate and create a stable foundation. Sheet pile driving requires skilled operators and careful planning to ensure proper alignment, adequate penetration depth, and interlock between adjacent sheet piles. Engineers consider soil conditions, groundwater levels, and the anticipated loads to determine the appropriate sheet pile length and design. The process may involve pre-drilling to facilitate driving in dense or hard soil layers. During sheet pile driving, vibrations and noise are inevitable. To minimize the impact on the surrounding environment, noise barriers, vibration monitoring systems, and appropriate mitigation measures are employed. Environmental regulations and community concerns often dictate the implementation of noise and vibration control measures. Board piling is a widely used construction method for creating deep foundation systems that provide support and stability to structures. It involves the use of specialized equipment and techniques to install piles, which are long cylindrical columns made of reinforced concrete. This article will discuss the various steps involved in the board piling method, from stakeout and referencing to the area cleaning process. The first step in the board piling method is the stakeout and referencing of the proposed pile location. This involves marking the exact positions where the piles will be installed according to the construction drawings and specifications. Accurate stakeout ensures that the piles are placed in the correct locations and are aligned with the intended structural design. Once the stakeout is complete, the next step is pre-boring using a drilling bucket. A hydraulic drilling machine is typically used for this purpose. The drilling bucket is attached to the drilling machine and is lowered into the ground at the designated pile location. The bucket is then rotated and drilled into the soil, creating a hole of the required diameter and depth. To maintain the stability of the borehole during the drilling process, a temporary casing is driven into the ground by gravity. The casing, usually made of steel, helps prevent the collapse of the borehole walls and maintains the integrity of the hole. The casing is driven into the ground until it reaches a stable soil layer or the design depth. Once the temporary casing is in place, drilling continues below the casing. A polymer-based slurry is commonly used during this stage to stabilize the borehole and facilitate the drilling process. The slurry, which is a mixture of water and a polymer additive, helps to prevent the collapse of the hole and provides lubrication for the drilling equipment. The installation of rebar cages is a critical aspect of the board piling method, ensuring the structural integrity and load-bearing capacity of the piles. In this method, it is common to use 3 rebar cages per one pipe to provide enhanced reinforcement. The rebar cages, which are prefabricated structures, consist of steel reinforcement bars arranged in a specific configuration. These rebars are designed to distribute the load evenly and withstand bending, shear, and axial forces. By reinforcing the pile, they enhance its strength, durability, and resistance to external forces. During the installation process, the rebar cages are carefully positioned within the borehole after the drilling and temporary casing stages. The first cage, known as the starter cage, is placed at the base of the borehole to serve as the foundation for the subsequent cages. After the starter cage is in place, the remaining cages are sequentially lowered into the borehole. Each cage is aligned and connected to the previous one to create a continuous reinforcement system. The cages are designed with interlocking features or connecting splices to facilitate the connection and maintain the integrity of the reinforcement. During the installation, it is important to ensure the vertical alignment and spacing of the rebars within the cages. Proper alignment guarantees that the rebars are positioned correctly to effectively resist the applied loads. In some cases, additional elements such as stirrups or spirals may be incorporated into the rebar cages. Stirrups are typically used to resist shear forces and prevent diagonal cracking, while spirals enhance the ductility and resistance to torsional forces. Following the installation of the rebar cages, a tremie pipe is inserted into the borehole. The tremie pipe is a long, narrow pipe with a funnel-shaped hopper at the top. It is used to place the fresh concrete into the borehole. The pipe is lowered into the borehole until it reaches the bottom, and the concrete is poured into the hopper. As the concrete flows through the pipe, it displaces the slurry and fills the borehole from the bottom up. This ensures that no voids or air pockets are formed in the concrete and that it is properly compacted. During the concrete placement process, several tests are conducted to ensure the quality of the concrete. One such test is the slump test, which measures the consistency and workability of the fresh concrete. The slump test involves filling a standard slump cone with concrete, compacting it, and then removing the cone. The difference in height between the top of the cone and the height of the concrete slump is measured to determine the slump value. The slump value helps assess the flow properties of the concrete and ensure that it meets the required specifications. In addition to the slump test, sounding is performed to check the integrity of the concrete. Sounding involves tapping the sides of the pile with a hammer and listening for any hollow or void sounds. A solid, dense sound indicates that the concrete has properly filled the borehole without any significant defects or voids. Once the concrete has been placed and tested, the tremie pipe is slowly lifted out of the borehole. This process allows the concrete to settle and prevents any disturbance or segregation of the concrete. The tremie pipe is carefully removed, ensuring that no excess concrete is left behind. After the removal of the tremie pipe, the temporary casing is gradually extracted from the ground. This process is carried out slowly to minimize any disturbance to the surrounding soil and to maintain the stability of the pile. The extracted casing is typically cleaned and reused for future piling works. Finally, the area around the completed pile is thoroughly cleaned. Any excess concrete, slurry, or debris is removed to ensure a clean and safe working environment. This step is important to maintain the integrity of the construction site and to prevent any potential hazards or obstructions. Pile head cutting is a crucial process in construction and civil engineering projects. It involves the removal of the top portion of a pile after it has been driven into the ground. The pile head cutting process is necessary for various reasons, including adjusting the pile length to the required height, facilitating further construction or retrofitting, or preparing the pile for load testing. To carry out pile head cutting, construction workers often utilize a hydraulic jack assembly system. This system is designed to provide the necessary force and precision to cut the pile head effectively and safely. Let's delve into how the hydraulic jack assembly system works and its components. The hydraulic jack assembly system typically consists of several components, including a hydraulic jack, a cutting tool, a support frame, and a power source. The hydraulic jack is the central component of the system, responsible for generating the force required to cut through the pile head. It operates using hydraulic pressure, which is created by a power source such as an electric motor or a diesel engine. The process of pile head cutting using a hydraulic jack assembly system begins with the workers measuring the desired length of the pile to be cut. This measurement ensures that the pile will be adjusted to the required height or be prepared for further construction activities. Once the length is determined, the workers mark the position on the pile where the cut will be made. Next, a concrete cutter is employed to create a circular cut around the marked position. This circular cut defines the area from which the pile head will be removed. The concrete cutter is carefully guided along the marked line to ensure an accurate and clean cut. After the circular cut is complete, the hydraulic jack assembly system comes into play. The support frame is positioned securely around the pile, providing stability during the cutting process. The hydraulic jack is then connected to the cutting tube. As the hydraulic jack applies pressure, the cutting tool starts to penetrate the concrete and steel of the pile head. The hydraulic pressure provides the necessary force to break through the material, allowing the cutting tool to progress steadily. The cutting process continues until the entire pile head is separated from the remaining pile. Once the pile head is fully cut, it can be removed using appropriate lifting equipment. The hydraulic jack assembly system may also include additional features to facilitate the removal of the concrete end. These features could include gripping mechanisms or attachments that can be affixed to the end of the pipe to pull out the concrete section efficiently. The construction of prefabricated reinforcing bars for bridge piers involves a systematic process to ensure their proper installation and structural integrity. At the construction yard, the prefabricated reinforcing bars are assembled according to the project specifications. These bars are designed to provide strength and support to the bridge piers, which are critical components of a bridge's superstructure. To lift and install the prefabricated reinforcing bars, a rough terrain crane with a lifting capacity of 80 tons is utilized. The crane is capable of handling heavy loads and maneuvering on challenging terrains, making it suitable for this construction task. The crane is carefully positioned near the specified installation area, ensuring stability and safety during the lifting process. When suspending the prefabricated reinforcing bars, several factors are taken into consideration to guarantee their proper alignment and structural performance. These factors include the potential deformation and yielding of the rebars, as well as the misalignment of the rebar arrangement. To address these concerns, rebar reinforcements made of equal angle steel measuring 65 by 65 are utilized. The rebar reinforcements are strategically placed and fixed to the main rebars in the vertical direction using fixing metal fittings. This additional layer of reinforcement helps enhance the overall strength and stability of the bridge piers. The suspension fulcrum, which serves as the point of support during the lifting process, is positioned on the rebar reinforcements. This ensures that the load acting on the suspension fulcrum is distributed evenly, minimizing any potential stress concentration points. To further optimize the lifting operation and ensure proper placement of the prefabricated reinforcing bars, a chain block is employed. The chain block is connected to a suspension support material, typically made of H steel, which allows for height adjustment during the lifting process. This height adjustment mechanism enables precise positioning of the prefabricated reinforcing bars at their designated location. With the chain block, the prefabricated reinforcing bars are carefully lifted and maneuvered into place at the predetermined position. The lifting process requires skill and coordination from the construction crew to ensure the safe and accurate installation of the bars. The crane operator, riggers, and other team members work together to monitor the lifting operation and make necessary adjustments as required. Once the prefabricated reinforcing bars are in their final position, they are securely fixed and connected to the existing structural elements. This is typically done using welding techniques or mechanical fasteners, ensuring a strong and durable connection. The installation process is meticulously executed, adhering to industry standards and project specifications to guarantee the structural integrity and safety of the bridge piers. The installation of box girders on the Tangerang-Merak toll road, undertaken by the Wagner Indonesian Bureau, stands as a remarkable example of engineering prowess and innovative thinking. This project successfully executed the installation process without disrupting the flow of traffic, showcasing Indonesia's expertise and advancements in the construction industry. Box girders are critical components in the construction of elevated highways and bridges, providing structural support and stability. Traditionally, installing box girders necessitates the closure of sections of the road or the redirection of traffic, resulting in inconvenience and delays for commuters. However, the Wagner Indonesian Bureau devised a brilliant strategy to minimize these disruptions. Firstly, meticulous planning played a crucial role in ensuring the seamless execution of the project. Extensive surveys and studies were conducted to assess traffic patterns and determine optimal timeframes for installation. By analyzing peak traffic hours and identifying periods of lower traffic volume, the team was able to pinpoint suitable time slots for the installation process. Another key factor in the success of this project was the implementation of an innovative construction technique known as the incremental launching method. This method involves constructing the bridge segments adjacent to the main span and then gradually sliding them into place. By doing so, the need for temporary road closures was significantly reduced. To accomplish this, the Wagner Indonesian Bureau utilized specialized equipment, including hydraulic jacks and launching trusses. These tools allowed them to precisely control the movement of the box girders and ensure a smooth and accurate installation process. The careful coordination and synchronization of these operations minimized disruptions to traffic flow.
Tilt-up construction is a streamlined, efficient method of building that brings many benefits, particularly for large structures. Preparation begins with the foundation work, where all necessary materials and equipment are gathered. Workers set up panel forms directly on the floor slab. These forms are the molds that shape each wall panel, including spaces for doors and windows. Steel reinforcement bars are placed within each form to provide structural integrity. Lifting inserts and embeds are added, allowing the panels to be hoisted later during assembly. Concrete pouring and insulation. Concrete is poured into the forms to create each panel. For insulated tilt-up panels, sandwich insulation is placed within the concrete to ensure continuous edge-to-edge thermal insulation, enhancing the building's energy efficiency. Panel lifting. Once the concrete has cured and reached sufficient strength, a crane lifts each panel upright from the slab. The panels are positioned and braced securely, one by one, until the building's exterior structure is complete. Finishing and caulking. In the final stage, exterior wall finishes are applied, and joints between panels are caulked to prevent water intrusion. This completes the building's enclosure, giving it a polished appearance. Tilt-up construction is valued for its speed, cost efficiency, and durability, making it an excellent choice for warehouses, schools, and other large facilities. Tilt-up construction is a process where large concrete panels are cast directly on-site and then raised into position by a crane. To start, reinforced concrete slabs are poured horizontally on a prepared surface. After reaching adequate strength, the forms are stripped from the panels, which are then readied for lifting. Workers attach lifting clutches to inserts cast in the panel, ensuring a secure hold as cables are tensioned. A crane tilts the panel upright, using a spreader bar to adjust rigging and accommodate various panel sizes. With hand signals guiding the crane, the panel is carefully set onto the foundation, where shims allow for precise height adjustments. Once positioned, temporary braces are installed to secure the panel during the rest of the shell construction. When the braces are firmly attached, tension on the lifting cables is relaxed, and workers disconnect the rigging. Panels are then braced and tied into the building's roof framing. The crane moves to lift the next panel, repeating the process until all are erected. Though originally used mainly for warehouses, tilt-up construction is now popular with developers and contractors across many types of projects due to its efficiency and cost-effectiveness. The Eurasia Tunnel, located in Istanbul, Turkey, is a unique engineering marvel designed to ease transportation between the city's European and Asian sides. Istanbul holds the distinction of being the only metropolis spanning two continents, which presents both a cultural richness and a persistent transportation challenge. Rapid urban growth and increased vehicle traffic have underscored the need for innovative solutions to connect the city's European and Asian districts and alleviate congestion. The Eurasia Tunnel was conceived as a solution to these issues, serving as a dedicated route for light vehicles to cross the Bosphorus Strait underwater. The Eurasia Tunnel extends over 14.6 kilometers, linking Kazlıçeşme on the European side to Göztepe on the Asian side of Istanbul. The first segment, spanning 5.4 kilometers, lies between the Kazlıçeşme intersection and Katladi Kapı on the European side. In this section, existing roads were widened, intersections were optimized, and access roads were improved to facilitate smooth traffic flow. This segment enhances access to the nearby rally areas and is part of the broader network of infrastructural improvements that ease entry into the tunnel. The core component of the tunnel, however, is the Bosphorus crossing. Measuring 3.4 kilometers, this section was excavated with a specialized tunnel boring machine, TBM, custom-built by Herrenknecht in Germany for the unique challenges of the Bosphorus seabed. The TBM had a record-breaking diameter of 13.7 meters, ranking it 6th globally, and was designed to withstand up to 11 bar pressure, the second highest resistance for such machines worldwide. This high-pressure tolerance was crucial for the tunneling under the Bosphorus, as the route passes through varying rock layers and sections with different pressure strengths, creating challenging underwater conditions. To execute the underwater tunnel crossing, reinforced concrete segments with high-pressure resistance, 70 megapascals, were used to ensure complete watertightness. These concrete segments form the outer structure of the tunnel, shielding it from the enormous water pressures under the Bosphorus. In response to Istanbul's seismically active zone, two specially designed seismic seals were incorporated along the tunnel's route. This innovative approach in the TBM tunneling industry ensures resilience against potential earthquakes, further enhanced by the multidimensional safety features and high-strength materials employed in the tunnel design. The tunnel construction was also notable for the world's first saturation diving maintenance on a TBM under such high pressure. Specially trained divers performed critical maintenance tasks under these conditions, making the Eurasia Tunnel a rare engineering accomplishment in terms of both technology and safety. The Eurasia Tunnel stands as a testament to Istanbul's drive to blend historic legacy with modern solutions. Its innovative engineering, commitment to safety, and sensitivity to the environment have garnered multiple international awards, reflecting Turkey's ambitions on the world stage. With its long service life and state-of-the-art technology, the Eurasia Tunnel is not just an infrastructure project, it represents a forward-thinking solution for urban transportation, designed to meet the needs of a growing dynamic city. The TBM progressed at a rate of 8 to 10 meters per day, working around the clock to ensure timely completion of the project. Meanwhile, sections on land used various construction methods based on geographical requirements. For instance, on the European side, the cut-and-cover technique was utilized for tunnel segments, while on the Asian side, 200-meter open close box sections were constructed, including a 165-meter transition box. The tunnel is a two-level structure, with one level dedicated to each direction of traffic. This double-decker design is 62 meters below the seabed at its deepest point. Every 200 meters, the tunnel is equipped with emergency evacuation passages, and waiting areas are available every 600 meters. Automatic toll booths and a main control building manage the tunnel's operations, ensuring smooth and efficient use. The tunnel is designed solely for light vehicles, with additional provisions to ensure continuous 24-hour service. One of the core aspects of the Eurasia Tunnel project was its environmental and social commitment. The project was awarded the Best Environmental and Social Practices Award in 2015 by the European Bank for Reconstruction and Development, EBRD, recognizing its minimal environmental impact and efforts to preserve Istanbul's cultural heritage. The tunnel's construction was carefully managed to avoid affecting Istanbul's historical areas, a factor that played a crucial role in its positive reception by both environmental and urban life advocates. The Eurasia Tunnel has significantly reduced travel times between Istanbul's European and Asian sides, cutting the previous 100-minute journey down to just 15 minutes. The tunnel is expected to handle up to 100,000 vehicles daily, easing congestion on alternative crossings and helping relieve the pressure on Istanbul's other major routes. Upon completion of its 55-month construction, the project entered a build-operate-transfer (BOT) agreement, allowing the operator to manage it for 25 years and 4 months. The Turkish construction company Yapı Merkezi and South Korea's SK Group, among other engineering firms, led the project, which received approximately $960 million in funding through an international credit package with a generous 18-year financing term.
Mobile cranes play a crucial role in the erection of 50-meter rob plate girders during bridge construction projects in India. These cranes are indispensable in handling heavy loads and providing the necessary lifting capabilities to ensure the safe and efficient installation of these massive steel structures. When it comes to erecting large bridge girders like the 50-meter rob plate girder, mobile cranes offer the flexibility and mobility required for the job. They can be easily transported to the construction site and set up in the desired location. Mobile cranes come in various sizes and configurations, allowing for customization based on the specific requirements of the project. The installation process of 50-meter rob plate girders involves multiple steps, and mobile cranes play a pivotal role at each stage. Firstly, these cranes are used to unload the prefabricated girders from transportation vehicles, such as trailers or flatbed trucks. Due to their high lifting capacity, mobile cranes can handle the weight of the girders and position them precisely for further installation. Next, mobile cranes are employed to lift the girders and position them accurately in their designated places. This requires precise coordination and skilled operators who can maneuver the crane with precision to ensure proper alignment and fit. The ability to rotate and extend the crane's boom allows for flexibility in reaching different areas of the construction site. Once the girders are in place, mobile cranes assist in securing them by connecting various components, such as bolts, plates, and welds. These cranes offer stability and control during this crucial process, ensuring that the girders are securely fastened to withstand the loads they will bear once the bridge is completed. Mobile cranes also play a vital role in the final stages of the installation. They are used to lift and position auxiliary equipment, such as formwork and scaffolding, which are necessary for subsequent construction activities. The versatility of mobile cranes allows them to handle different types of equipment, making them essential for the overall bridge construction process. Safety is of paramount importance during the erection of 50-meter rob plate girders, and mobile cranes are equipped with advanced safety features to ensure the well-being of the workers and the integrity of the structure. These features include load monitoring systems, outriggers for stability, and operator training to adhere to proper safety protocols.